So welcome to the 45th Theoretical Physics Colloquium by Professor Andrei Beloborodov, who's a professor at Columbia University. He got his PhD in astrophysics from Lebedev Physics Institute in Moscow, Russia. He had several junior and postdoctoral positions, starting from Lebedev Physics Institute, moving to Stockholm Observatory for a couple of years, and then staying at Stockholm Observatory as a research associate between 1999 and 2001. He became a senior research associate at Canadian Institute for Theoretical Astrophysics in Toronto, Canada, between 2001 and 2003. And then he accepted a faculty position at Columbia University. He is a full professor since 2011 at Columbia University. Over the years, he received a number of different honors and awards, starting from Beatrice Tremaine Fellowship from the Canadian Institute for Theoretical Physics in 2002, Alfred Sloan Research Fellowship in 2003, Marco Kingsley Distinguished Visitor at California Institute of Technology in 2012, Simons Investigator Award in 2016, and finally in 2019, Humboldt Prize. So his research interests include theoretical astrophysics, gravitational waves, cosmology. He is well known for studies of compact objects such as neutron stars and black holes, physics of gamma ray bursts and magnetars. And today he will be talking about magnetars. And with that, I'll give the microphone to Andrei. Go ahead.
Okay, thank you for this introduction. My topic today is magnetars, and these are strongly magnetized neutron stars. So I'll start with this little picture of a simulation that shows an initial state of the magnetic field in one model, how a neutron star is born with very strong magnetic field, up to 10 to the 16 counts. These strong fields end up from flux conservation as the star collapses, as a progenitor star collapses into a neutron star, compressing the magnetic flux with it. And in addition, there can be dynamo mechanism that amplifies magnetic fields to up to 10 to the 16th, maybe even high values. So we observe these ultramagnetized neutron stars as very active X-ray sources. We know about 30 of them in our galaxy. This is the top view of our galaxy, the Milky Way. And you can see many blue crosses, which are ordinary neutron stars, normal radio pulses. And red symbols are magnetars. They are active, producing X-ray bursts and other stuff that I'll talk about later in my talk, for about 10 kilo years, which is small time compared to typical age of regular pulsars, millions of years. So even though we don't see, we see only a few tens of them, in fact, at least 10%, maybe up to 50% of all neutron stars are born as magnetars. About one third are found in supernova remnants. So we see that these objects are really products of stellar collapse, which also produces supernova explosion initially and a supernova remnant. None of them are found in binaries, so these are isolated objects. Their rotation periods that we observe are between 2 and 12 seconds, which is slow for their age. And actually, from the observed spin-down rate, it's one way of measuring magnetic fields, actually, from the spin-down rate of a neutron star. If you measure its period and time derivative of period, you can actually estimate the magnetic field. And this is how we can see that the fields go up to 10 to the 15th in the dipole component of the neutron star. And we suspect even stronger fields inside the star, hidden inside the star, up to 10 to the 16 counts. Okay, these objects are very hot, unusually hot. You see here, well, it's a busy plot, but basically you see many different, a few different classes of neutron stars, and magnetars are shown by red symbols. And so we can see the thermal luminosity, or the surface temperature, if you like, thermal luminosity scales as temperature to the fourth. This surface luminosity exceeds 10 to the 35 erg per second in some cases. And so all these red data points lie above other known typical, Newton stars in supernova remnants, pulses, etc. So they are hot. They're also bursting. That's a remarkable feature, and that's how mostly we discover them now. These magnetars are producing X-ray bursts. Typical duration of an X-ray burst is about 0.1 second. And luminosity can go for regular burst up to 10 to the 42 ergs per second. And sometimes these objects produce giant flares with luminosities up to 10 to the 47 ergs per second. For comparison, the luminosity of the sun is 4 times 10 to the 33 ergs per second. So these are tremendously bright objects. And from this output that we observe, you can estimate the total energy budget that you need over the lifetime. And then you find a number emitted in X-rays, something like 10 to the 48 erg. And assuming reasonable efficiency of, I'll talk a little bit about this later, you can conclude that about 10 to the 49, maybe 10 to the 50 erg is hidden inside the Newton star in the form of magnetic energy that feeds the observed activity. This is just one slide to show how remarkable the giant flares are. Basically, these are luminosity at the peak goes up to 10 to the 47 ergs per second. Total energy emitted during the main peak of the flare and its oscillating tail can go up to 10 to the 46 erg. The peak lasts a few tenths of a second and the tail goes for 6 minutes. And we see about the same structure of the giant flare in 3 different flares observed by now, giant flares. Another interesting observational aspect to conclude this really brief review of phenomenology of magnetars. During the flare, periodic, quasi-periodic oscillations have been detected, high-frequency oscillations, up to kilohertz range. So you can see this Fourier spectrum. So you can see peaks here, which represent quasi-periodic oscillations. And the theoretical picture of these oscillations is on the right. So the star is excited during giant flare and it begins to oscillate. And by analyzing, by comparing the observed quasi-periodic oscillations with the theoretical models, it was concluded that there should be a superfluid neutron core inside the star. Well, we know that neutron stars contain neutron cores, that's why they're called neutron stars. But also, you can conclude that magnetars and more generally neutron stars, which are not too hot, are superfluid. And this fact is actually was deduced also from this quasi-periodic oscillation, simply because when the star oscillates, its magnetic field, its plasma component, electron proton component are coupled together and they oscillate. But the neutrons, because they're superfluid, they're decoupled and don't contribute to the effective oscillating mass. That's how you can see this in the analysis of QPOs, quasi-periodic oscillations. All right. So the basic feature of magnetars is there is a lot of magnetic energy caged in the Newton stars, simply because neutron stars, even though they're called neutron stars, they're excellent conductors. There is enough plasma, and it's a very conducting medium, both the core and the crust of the Newton star. And so magnetic energy is trapped. Magnetic field is frozen into this excellent conductor. And if you want like a brief summary of the story of magnetars, the main drama is basically the desire of the magnetic energy to get out from the star. If you imagine for a second that the star is not there, annihilated, what would the magnetic energy do? This 10 to the 50 erg, just explode, just expand. That's what electromagnetic field would like to do. But because it is frozen into this heavy conducting medium, it stays there. And it finds its way out gradually and slowly. It has to be sly and tricky to get out. And there are a few stages of getting out. So I will discuss them in turn. So there is a core, some interesting dynamics is happening. There is a crust of the star. There is a magnetosphere around the star, external magnetosphere, and then there is a wind zone from the star. Okay, so let's start with the core. Okay, so this slide that showed how quasi-periodic oscillations are observed on the left and how theoretical models predict these oscillations on the right. Okay, so I talked about inferring that the core is superfluid from comparing theory with observations. This little image, can you see now slide switching? Okay, I'm on the next slide now.
Yes.
Okay, so you see the little cage and there is magnetic energy hidden. Good. So, so the magnetic field is literally caged and it tries to get out. That's what I tried to explain. And if it happens again, Igor, if you can just let me know, we'll do this again because I don't know what's happening with Zoom.
Absolutely.
Okay. Nice. Okay, so let's move on then. So I would like to talk about the core. And the basic process there is ambipolar diffusion. So, okay, the star is born very hot, 10 to the 11th Kelvin temperature, and it behaves as a single fluid initially. Neutrons and protons are colliding very frequently, and they're all coupled together. The magnetic field is coupled to electron-proton component. However, later, the star cools down, and the very degenerate stuff that forms electrons, neutrons, and protons, because it's degenerate, particles, particularly neutrons and protons, collide much less frequently. The free path of particles, degenerate particles, becomes large, and now electrons and protons can move with respect to neutrons with some rate. Now, the reason why they would like to move, there is a J cross B force, the Ampere force. Of course, there is J in the star because there is B. J is the current density. B is the magnetic field. So you cannot have a force-free configuration there. So there is a component of J cross B, vector product of current and magnetic field. And that's the force that would like to move the magnetic field, essentially, magnetic field and plasma out of the star eventually. There is also a force that opposes that, the frictional force, the electrons and protons are colliding with neutrons. And so the result, there is a force balance between friction and Ampere force, J cross B. As I said already, the time scale for proton-neutron collision depends on temperature. And therefore, the balance, this equation, which determines the velocity of the electron-proton fluid, and therefore the velocity of the magnetic field lines that are vectored together with electron-proton fluid, this velocity depends on temperature of the star. In turn, temperature is controlled by the balance between heating, which comes from ambipolar diffusion, this frictional force, is a dissipative, results in dissipation. So there is heating released by ambipolar diffusion. So this drift process is called ambipolar diffusion. It produces heat. On the other hand, the core is cooled by neutrino emission. And the main cooling process is so-called modified Rooker reactions. So there is direct Rooker reactions when electrons combine with protons into neutrons and neutrino, and then there is the opposite process of decay of neutron into proton and electron. And so when these processes happen frequently, they steal energy. It's called Rooker reaction. So modified Rooker is similar, but it involves another particle, becomes free body reaction, spectator nucleon, which can take the excess of momentum when direct work is prohibited because there is an energy gap for direct work. So anyway, so this is the process which is very sensitive to temperature of the neutron star. And it can be very efficient cooler at high temperatures when the star is young. Okay, so that's what's happening basically. The star is cooled by neutrinos and it's heated by ambipolar diffusion. There is an additional cooling process which becomes important when the star goes through its temperature drops below the critical temperature for Cooper pairing of neutrons. So then it becomes superfluid, but it takes some range of temperatures and Cooper pairs form and reform and producing neutrinos and antineutrinos during this state when the temperature is between 0.3 and 1 of the critical temperature. So actually, during this transition, the cooling rate is enhanced. So anyway, these processes are relatively well understood, and one can estimate the thermal evolution of the star. And basically, we're dealing here with the couple problem of how the star is heated by ambipolar diffusion and cooled, and the self-consistent evolution here can be estimated. This plot shows the result with just modified Ricke reactions without superfluidity. The characteristic temperature is about 10 to the 9th Kelvin, a little bit below it. It's very hot core. The dotted line shows what would happen if there are no ambipolar diffusion. The star would just cool down. When ambipolar diffusion switches on, the magnetic energy converts to heat partially and offsets the neutrino cooling. And for a while, for centuries actually, there is a balance between ambipolar diffusion heating and neutrino cooling. Okay, so you see this flat part. And eventually it ends and ambipolar diffusion is choked and you have transition to superfluidity, etc. So this stage lasts roughly 1,000 years, but actually I'll come back to this point. If the star is especially strongly magnetized, it can last only a few decades. And then you expect a particularly violent ambipolar diffusion. You can see that here, the stronger is the diffusion, the stronger is the heating, and the shorter is the lifetime of this process. Observationally, when you look at this object heated at the core, you get some heat diffusing to the surface. So most of the produced heat escapes in neutrinos, but because the core is hot, you also have heat conduction. And on a time scale of several months, the heat reaches the surface and establishes quasi-steady state thermal conduction. The thermal conductivity is lowest in the upper layers of the crust. And so it's like a blanket around the star. And this, the properties of this blanket have been studied very much in some detail and well known, particularly by St. Petersburg group, Alexander Patekin. And so this plot summarizes the relation between the internal temperature of the star and its thermal luminosity from the surface. Depending on the composition of this blanket, it could be pure iron or it could be some light elements. You get some different results, but the bottom line is that you find that the surface temperature is comparable to 10 to the 6th Kelvin, while the internal temperature varies between 10 to the 8th and 10 to the 9th. Okay. So that's what comes out from ambipolar diffusion. There's the magnetic field tries to get out from the core, dissipates a lot of energy on the way. Most of it goes into neutrinos, and some of them, a small fraction, reaches the surface, and you see emission from the surface, thermal emission. Now, what's happening in the crust? In the crust, the magnetic field lines can also evolve because of the process that is called Hall drift. It's summarized by the simple equation. It basically states that magnetic field lines are frozen into electron fluid. So if there are electric currents flowing in the crust, there is current density J, you have some electron density N, E, which we know in the crust. We know all the properties of neutron star crust. density stratification, etc. And so VH is this so-called whole velocity of electrons. The electrons have very low mass, and therefore their rest frame electric field should be zero. This is the condition that is basically telling you that dB/dt, which we know is negative curl E, right, induction equation. So this electric field in the log frame is found from the condition that the electric field in the rest frame of the drifting electrons is zero. So E is negative B whole times B, okay? So this is basically induction equation. On the other hand, this equation states that B is frozen into the electron fluid, which may be moving with some VH. So the magnetic fields are being deformed. They follow the motion of the electron fluid through the crust. The crust is a solid, and therefore ions are static in the lattice, and the electrons are drifting through the crust. The time scale for this process can be easily estimated from these equations, and depending on the strength of the magnetic field and the scale of variation of B in the crust, can be 10 to the 4 years, relatively slow process, very well studied, especially in recent years, in three-dimensional simulations also. There is also such a thing as Hall waves. It's a simple example of this Hall drift. So when you imagine a radiation problem, you have vertical field in the z direction. Horizontal plane is parallel to the, let's say, surface of the star. Okay. And you look at how the perpendicular component of the magnetic field evolves in time. It's easy to derive, equations for this problem. And then you will see that this system supports waves described by this equation here, where capital DH is the Hall coefficient, so-called, which determines the dispersion relation for these waves. Because there is I, you see that the wave is going to rotate. The electric field, the magnetic field, is going to rotate in this wave. The dispersion relation also gives you the phase speed, omega over k, which grows with k. That means that the high k modes, with high wave number modes, are propagating fastest in these Hall waves, fastest at short wavelengths. Just to give you one simple example of how this process works in the crust. So imagine a liquid neutron electron core, and there is a boundary here, and above it you have crust. And suppose some bipolar diffusion has done its, some evolution of magnetic field, while the field is still frozen in the crust because it evolves on so longer time scale. Then you create this kink in the magnetic field lines. The field now has a kink, which means that there is a current sheet here at the interface of the core and the crust. And this is the initial condition for launching after this fast bipolar diffusion phase. It sets the initial condition for launching Hall waves into the crust. And the panels here above show this red curve shows the, well, you can think of it as the endpoint of the magnetic vector, this B curve. Initially it goes like this, and there is no B curve in the crust. This pink plane is the interface between the crust and the core. And as you let it go, this magnetic vector begins to rotate and grow. So you launch it, this circular propagating Hall wave into the crust. And as you can see, the short wavelengths propagate ahead of the long wavelengths. So it's just a simple example of how you create magnetic field evolution in the crust. What you also find is that it generates stresses, magnetic stresses in the crust. The product of BZ, vertical field, and B, horizontal, is the stress, magnetic stress. And this stress is applied to the solid crust. It's held by the solid. And at some point, another thing can happen. The crust can yield to the stress mechanically. So the whole drift itself is dissipationless, so it's very good. It's promising. The magnetic field has found a way of getting out, like diffusing its energy through the core up to the magnetosphere without losses. That's good. But on the other hand, it does create small-scale structure, which can become prone to ohmic dissipation, and the magnetic field begins to lose its energy. And it also can initiate mechanical failure. Just to explain quickly, it's another like basic building block of magnetar lives. Just a simple mechanism, like basic mechanism of how it can work. Imagine you have magnetic field threading the crust and it applies stress. And at some point it becomes intolerable for the crust, meaning that the solid yields in some layer. What happens then? The layer begins to flow plastically, and plastic flow is dissipative, you generate heat. And then this heat begins to be conducted out of this layer. And as the heat is conducted, it softens the material and it continues to yield to magnetic stresses. And you launch a wave. It's pretty much, it's very similar to deflagration wave. Like you use match to ignite fire, and then you begin to use energy. Basically, it's a instead of chemical fuel, we have here magnetic energy, which is being burned, the horizontal component of magnetic energy. And then you launch a front, which can dissipate this magnetic energy into heat. In extreme cases, when the field is strong, it can actually even melt the crust. And this green zone becomes so hot that this layer is melted. And of course, it allows this magnetic stress, like this field line, pulls the upper slab, and it allows the magnetic field line to relax to more vertical configuration here. So what happens in these waves is that you have motions, relative motion, horizontal motions in the crustal layers. So of course, in this way, magnetic field loses energy, dissipates part of the energy. But part of it succeeds and gets out of the star because these motions of the plates deform the magnetic field, that is external magnetic field that is attached to the neutron star. All right. So now let me talk about what happens in the magnetosphere. So the magnetosphere is deformed by these surface motions, crustal motions of the magnetar. As a result, it resembles solar corona in the following sense. The field becomes twisted, deformed, and it is pretty much force-free, what they call, in the sense that J is parallel to B. The solar corona is magnetically dominated, and also the magnetosphere of the neutron star, by definition, is strongly magnetically dominated. Magnetic field is the dominant form of energy there. It's very strong. Whatever particles are living in the magnetosphere, they are sitting in the zero Landau level, so they move strictly along the magnetic field lines. Whenever you try to excite the perpendicular motions, radiate it away immediately. And so suppose you have twisted up this external field. Before you do that, the magnetosphere, let's say, imagine a simple dipole configuration. It can be plasma-free. The hydrostatic scale height of the plasma layer on the surface of neutron star is a few centimeters, 1 to 10 centimeters. It's tiny compared to the radius of the neutron star, which is 10, 12 kilometers. So naively, you would say there is no plasma, there is exponentially reduced plasma density. However, and it's a difference from the solar corona, where you have plenty of plasma. However, when you begin to twist the magnetic fields, you ignite electron positron discharge, which fills the magnetosphere with plasma. The mechanism for this discharge is very straightforward. So you have you begin to accelerate seed particle. So electric field begins to accelerate seed particles to high Lorentz factors, and these seed particles upscatter whatever background photons are. The star emits KV photons, X-rays, and this particle can resonantly actually upscatter these photons. So when this photon is blue shifted to the breadstream of the particle, it can find resonance with the Landau energy, and then the cross-section for scattering becomes big. And that scattered photon gains energy of gamma squared, the electron Lorentz factor squared, and it can end up at energy much higher than electron rest mass. Then this photon easily converts to electron positron pair just off the magnetic field. high energy photons cannot live in strong magnetic fields. They convert to pairs. So that's how the discharge works. Here is a simulation which shows this discharge. So the simulation is actually symmetric, and we simply started to rotate slowly the part of the star, actually big part of the star, the upper hemisphere with respect to the lower hemisphere of the star. And then you see red is basically the electric current, which begins to flow. Here you see this black cavity which grows in size. Initially it was very small. So over time, and the process lasts, so what we see here in this, by the way, this is a particle itself, so-called simulations. Basically, we follow individual particles. We model plasma as a large number of millions of individual particles, and they move in self-consistent electromagnetic field. So the field lives on a grid, and E and B fields live on a grid, and particles are followed individually, and their motion determines the electric current that you put in the Maxwell equations of the source, and you can evolve the system self-consistent. And with this simulation also implemented this process of electron positron creation. When the photon background photon is upscattered and turns into a pair. And we do see that this system finds a way of conducting electric current when the magnetosphere is twisted. And of course, this process is dissipating because it requires a final voltage. If there is a threshold voltage to ignite the discharge, which is about, it's in the GeV range. The corresponding time scale to erase these electric currents resistively is like a year. As you can see by now, the cavity has expanded. It shows an interesting feature that actually the resistive process works kind of inside out. Basically, what's happening, the electric currents that used to flow along the magnetic field lines, the dipole field lines, they got erased and they are now closed below the surface. This is ideal to conduct the star itself. So the currents that flow up there, they're still there. They just close along the surface. And then layer by layer, like onion structure, you remove these currents. So you launch a front that erases electric current this twist in the magnetosphere on the year time scale. Okay, this is the theoretical picture of magnetospheric activity which results from surface motions of the magnetar driven by these internal processes and the pole diffusion and the observational outcome here is that, of course, this region produces no thermal X-rays, hard X-rays. And another, and by the way, this is just an example of hard X-ray spectrum. For magnetar, there is a quasi-thermal component that comes from the surface, and there is this beautiful no-thermal hard X-ray component, quite consistent with this theoretical picture. Twisted magnetosphere and its hard X-rays. I showed how this front erases the electric current flowing in the magnetosphere and how you can expect a hot spot at the footprint. These particles accelerated in the magnetosphere, then bombard the neutron star, and they produce a hot spot. And actually, you expect this hot spot to shrink with time as this front progresses, right? The spot becomes smaller and smaller. And similar shrinking hot spots are actually observed. So these are several objects where we started to show hot spot, so-called transient magnetars, and then over time scale consistent with expectations, months, years sometimes, the hot spots are shrinking with time. So it looks like we may be observing this process of untwisting. So now let me move to the wind part. I'll just comment briefly that any rotating neutron star magnetized should be producing a wind. This is the canonical picture of a wind. So omega is the rotation x, angular velocity of the star, mu is its dipole moment. And there is plasma around it, electron photons are created around this star. And without going into detail, just let me state here that that's the picture of the wind that you produce outside the light cylinder. The light cylinder is the distance from the rotation axis, where the co-rotation velocity is equal to the speed of light. So the plasma can co-rotate this yellow zone with the star inside the light cylinder, and it cannot rotate outside the light cylinder. Instead, it forms this pointing flux dominated outflow of kind of spiraling magnetic field lines with alternating polarity if magnetic moment is inclined with respect to omega. So inside the light cylinder there is closed zone. Outside the light cylinder there is a wind. This wind is loaded with pure plasma, electrons and protons. For magnetars, well, it's my estimate. There's not much work on how fast this wind should be. So here is a slide which shows just one basic point. I think that's the process of loading of open field lines that go to the light cylinder and then form this outflowing pointing flux. So I naught is the characteristic electric current that all normal pulsars have. The magnetic field lines are twisted at this light cylinder. They form this spiral as it flow out, and therefore there is electric current supported flowing through the light cylinder. This is I know. Magnetars carry much stronger magnetic currents, million times stronger in the closed zone, simply because they flow in the region of much stronger field. The light cylinder of the magnetars at values like 10 to the 10 centimeters, because they're not fast rotators relatively small second period. And so there's not much magnetic flux actually going through the light cylinder. This light cylinder is far, like 10 to the 4 times the radius of this. And this closed magnetosphere with stronger fields, which is strongly twisted, carry much stronger currents. And these currents are supported by electron Poisson discharge, which involves this photon production and conversion of photons into pairs. And so some of these photons convert to pairs also on the open field lines that eventually go to the extend to the light cylinder. And that's how you load plasma into the wind. And without giving you further details, it turns out you can estimate characteristic number of particles that can flow out, and it gives you a Lorentz factor of the wind that flows out. And it's a order of tens. It's pretty fast wind, but not as fast as in normal passes where you have fewer lower penetration rates. All right. So up to now, we went through the core dynamics, the crust, the magnetosphere, and the wind. And so far, the story was relatively sad, I would say, from the point of view of escaping. Like the magnetic field would like to escape, but doesn't really succeed escaping. Well, there is some flux outside the light cylinder, but it's tiny because the magnetic field is so small at the light cylinder, because the light cylinder is far away from the star. And whatever magnetic field managed to be transported from the core into the magnetosphere, it was erased by the dissipation caused by electron Poisson discharge. However, there is a process that can finally release magnetic energy into the outer space, and this process is magnetic reconnection. Of course, as long as magnetic field lines are closed and tied to the star, however you torture them, they still remain tied to the star. But magnetic reconnection is precisely the process that produces closed loops that are no longer connected to the star. So if you reconnect here, you can release this magnetic loop. This process is dissipative, magnetic reconnection, and here these opposite magnetic fields partially annihilate, so you lose fraction of the energy, but still you can expel significant magnetic energy as well. Now, there are a couple of ways. I'll show you a couple of simulations how this can happen. This is one axisymmetric simulation when, again, you take upper hemisphere of the star and begin to rotate it slowly with respect to lower hemisphere, twisting up the magnetic fields attached to the star. One thin line is, the color is J5, total triangles. One thin line is highlighted here, and it's like heavy black line. And as you begin to twist stronger and stronger the fields, the magnetosphere inflates. You can see that this particular thin line becomes more and more extended. And eventually, it opens up. And there is an instability, like when you impart magnetic twist in radians, something like 4 or 5, then this configuration becomes unstable. So you do it slowly, the field inflates, and then boom, at some point it becomes unstable, form a very thin current sheet separating opposite magnetic fluxes this way, right? And then there's current sheet between them. And this phenomenon is called magnetic collapse, and then becomes unstable to so-called tearing mode because this current sheet begins to break up into threads, current threads. And this is the reconnection process. You can see the simulation. So that's one way of doing that. The very high is what we think actually is happening in giant flares of magnetars, because this process is dissipative, and you release a lot of energy if it happens close enough to the star, where you have strong magnetic fields. And basically, you take a fraction of magnetic energy, convert it to heat. Suddenly, when the magnetic energy is so high, like B here is 10 to the 14, 10 to the 15th counts, you can calculate, and basically you convert it to heat. This energy is completely thermalized immediately. All the rates are huge, so you have, so this is called full thermodynamic equilibrium. You create electron-positron pairs in particular that correspond to the temperature, and you form an optically thick electron-positron fireball trapped in the magnetosphere of the star. And the typical temperature of this fireball you can estimate simply by equating blackbody radiation energy density to a fraction of magnetic energy density, and you get temperature for MeV. So that's why you have a lot of electrons and positrons there, because one MeV is above electron rest mass. Another way of producing reconnection and releasing magnetic loops from the star is much less energetic when you have a starquake. So what is a starquake? A starquake, usually what we mean by starquakes, magnetars in particular, is also earthquakes. It's similar. So you excite oscillations of the Earth. So here you excite shear oscillations of the crust. And this here is just one simulation done by Ashley Gransgrove in our group that shows, color shows the displacement into the plane of the figure. And you can see how this shear displacement grows near the surface of the star. Very similar to, and they propagate along the surface sideways, very much like so-called gallery modes, whisper gallery modes. It's similar physics here. The shear oscillations, once you create them, they go to the surface, they go along the surface, and they have highest amplitude near the surface of the star. And so the shear oscillations also deform the external magnetic field lines attached to the star. So they launch an alpha wave into the magnetosphere. And this alpha wave grows in amplitude as it propagates along external field lines. I'll show this other simulation. You see black lines, magnetic field lines, and there is a shear alpha wave that propagates and eventually expels a chunk of magnetic energy. You see reconnection behind this expulsion event, and you see a second alpha wave again doing the same thing. So basically, when you launch an alpha wave, which is initially small near the star, the amplitude may be 10 to the minus 3. As it goes up into the magnetosphere along extended field lines, its amplitude grows. To conserve the energy of flux, the background drops as 1 over r cube for dipole field, and therefore delta B over B, the relative magnetic energy, which it grows, and the wave becomes non-linear at large enough distances, then it just says goodbye to the star, essentially. It just feels like, okay, it's on its own. If my energy now exceeds the background energy, I can just keep flying ballistically away from the star. That's what they do. And behind them, there is a reconnection process. Okay, this I would like to say here just a couple of words about what kind of emission we may expect from these expulsion events in the outer magnetosphere, because I think they may actually explain the hard X-ray bursts that we see from our magnetars. Not the giant flares, but these regular, much more frequent bursts that I showed in the beginning. They typically peak in about 10s to 50 keV range, the spectrum, X-ray spectrum. They last 0.1 second. And so one possible explanation for these bursts is actually reduced to clean physics problem. You have magnetic field in a certain size, like 10 to the 7 centimeters, 10 kilometers or something, 10 to the 8 centimeters, maybe 100 kilometers. Sorry, 100 times 10 to the 8 would be 1,000 kilometers. And so you have this characteristic size and you have magnetic energy density. That's all you have in this problem. And imagine now that this reconnection process converts this magnetic energy into heat. On for reconnection, typically it's happening like 10 light crossing timescales of the system. So this problem has just one dimensionless parameter expressed in terms of magnetic energy UB and size of the system. Sigma T is Thomson cross-section. And so you can ask the question of in what form the energy will come out from this dissipation event. And to solve this problem, you actually, what I've done is just numerical simulation. So you basically begin to heat particles in the region. It doesn't matter how many particles you put in the beginning, there are few particles. It's almost like vacuum, but you put some seed particles there. And then you begin to heat them with a given rate, which results from dissipation of magnetic energy. There are some background seed photons, and these particles begin to, the accelerated particles, heated particles, begin to upscatter photons and generate secondary electron-positron pairs. And you can keep following the evolution of that system. It's basically a radiative transfer problem where you supply heat in a certain region and you follow how this heat in the form of photons tries to escape through a plasma which is self-consistently created by photon-photon collisions turning into electron-positron pairs. And as a result, what you find in these simulations is that this region, heated region, dresses itself into optically thick electron-positron cloud, and it self-regulates to sustain about 0.1 electron rest mass per photon. Because if you begin to, so basically the system produces enough photons, so when they share energy between them, not too many of them are above electron rest mass. Otherwise, they start to overproduce the number of pairs, and the pairs begin to produce even more photons. And this self-regulation, like feedback loops, make sure that the temperature is not too high. It brings temperature back to lower values. So there is a self-regulation process that controls the temperature in this system to a value of about 0.1 electron rest mass. It also controls the number density of electrons and positrons, tiny number, about 10 to the minus 5, with respect to the photon density that the system generates. And you can find from this kind of simulations, you can also find the position of the photosphere of this cloud from which photons escape freely. And you can find the spectrum that escapes. And here is a theoretical spectrum. So this is the spectrum that will be emitted by an X-ray burst produced by reconnection process and ejection of magnetic loop from the star in the outer magnetosphere. And the bursts, the observed X-ray bursts are actually not, I mean, they're similar. I mean, they peak at a similar energy. So you can see here one example. Bursts have spectra varying a little bit, but they always peak in hard X-ray band, typical magnetar bursts. All right, so I have maybe 5 more minutes, right? Or a few minutes. So I'd like to talk briefly about this new emerging connection between magnetars and so-called fast radio bursts. So the basic idea here is that maybe there are young hyperactive magnetars in distant galaxies which are producing these enigmatic fast radio bursts that we see. These fast radio bursts are gigahertz bursts. They have millisecond duration. They're extremely bright. They have luminosities up to 10 to the 42 x per second. They occur in distant galaxies. Their rates are more than 10 to the 4 per day per entire sky. And on cosmological grounds, they're discovered only recently. It's a major development in astronomy, in particular radio astronomy, since discovery of pulsars. They have been associated with magnetars immediately after discovery, so discovery of FRBs, based on the rates and the fact they have millisecond duration. So you begin to think of what kind of source could possibly produce such a burst, and it's got to be a compact object. So the first, many of these bursts are repeating. The first repeater was discovered well, it was localized in 2016 in a distant galaxy. And I think the most plausible explanation for this repeater is the young hyperactive magnetar. So basically it all comes to that picture of how a young magnetar could have ambipolar diffusion in the core that I talked about in the beginning, proceeding very quickly and energetically, like producing all this activity, including flares on a short time scale, but with very high rates. We don't see these objects in our galaxy. All the magnetars we see are relatively old, all these 30 objects, kiloyear roughly old, and older up to 10 kiloyears. But they used to be young, and maybe they had, imagine in distant galaxies, they could have even stronger fields than our local magnetars. And these objects are expected to be hyperactive. So what would they do? They will do these flares very frequently. So it turns out that after working a little bit in this direction, you actually can identify many ingredients that you need to explain phenomenology of FRBs. And let me just briefly talk about a couple of things. So one is this observed periodicity of one repeater with this name discovered in 2018. And it has 16-day periodicity in the sense that its activity switches on and off. It produces multiple bursts, then it can switch off and then reappear again. But when you look at phases at which it is active, they always follow a certain window within a 16-day period. And so one possibility which falls nicely into this magnetar interpretation is that it's a precessing magnetar. Local magnetars, normal magnetars in our galaxy, they don't precess because they are most likely superfluid. They are old enough to be cold enough to become, for neutrons to become superfluid. Superfluidity does not allow precession because what would happen? Well, superfluid core, a rotating core, vorticity is quantized. And so you have this array of vortices. If the star tries to precess around the angular momentum, you basically try to push the crust and with the magnetic field, which would have to cut through the vortex lines. It most likely would be dissipative process. It's not really allowed. However, if your star is not superfluid, that is, it is hot enough, that is, the magnetar is hot enough to be not superfluid, then it can precede, it actually expect precession. This precession period is determined by how strongly the star is deformed, and it is deformed by Hooke stresses of the magnetic field, and field of 10 to the 16 Gauss, expecting magnetar is deformed at this level, 10 to the minus 5. And then you get a period of precession of about days to months, which is consistent with the observed precession period. And finally, the last thing is that there's a natural mechanism that should be working in these hyperactive magnetars producing fast radio bursts. Bright radio emission must be produced by a coherent emission process. And this emission process actually does exist in the blast wave, which is produced by a magnetic explosion driven by this plasmoid, this chunk of this magnetic loop that was ejected, that I talked before about, right? So this eject magnetic loop, it accelerates to very high Lorentz factor. It drives the explosion, like solar flares drive explosions in solar wind. The only difference from solar flares here is that the whole thing is ultra-relativistic. The pre-explosion wind is ultra-relativistic, and the blast wave driven by this ejected plasmoid is ultra-relativistic. The characteristic Lorentz factor is like thousands for the blast wave, which allows, of course, the emission to be Doppler compressed in time, and that's why we observe 1 millisecond duration. Okay, so the coherent mechanism is basically my last slide, I think, is the, well, it just illustrates how this coherent radio emission is produced when you have a shock in magnetized medium. Particles crossing the shock begin to gyrate in the post-shock field, and they form a ring in momentum space. So they form a kind of maser structure. You see inversion here, right? So a lot of particles in higher Landau levels. And this ring is unstable to bunching. And as a result, you produce coherent radio emission on a with frequency which scales with simply gyro frequency of this ring, frequency of gyration in the post-shock medium. And there are plenty of simulations by now, and we are working with detailed simulations also that show elaborated details of the properties of this wind, like radiative efficiency, polarization, etc. All right, skip this. These FRBs, they have very strong, they produce strong electromagnetic waves. Their strength parameters can be way above unity. And this is what people play with lasers now. So there is a lot of parallel physics here and questions which are not answered for FRBs yet, like modulation and stability, fermentation and stability, how this ultra-strong wave tries to propagate through the plasma, the wind, as it tries to escape. And finally, this is just to give you an exciting observational result, which came out a little less than 1 year ago. This is the first detection of an FRB from a local magnetar. So before 2020, April, it was all speculative, the idea that magnetars produce FRBs, but now we know that actually they do. So one of the FRBs was detected. It was a relatively weak burst, but still it had millisecond duration. It coincided with an X-ray burst. And except for its brightness, it looks like normal fast radio burst. So here's my summary. Basically, magnetic energy does succeed to escape over time from the star, but it's doing that with big dissipation losses. Okay, starting from the core, that's the first process that allows the field lines to move, magnetic field to move out from the star, from bipolar diffusion. Most of it is wasted. It's wasted into neutrino emission. We are fortunate that there are these dissipation processes because this quest of the magnetic energy to get out from the star, if it does so easily, it would be completely silent for us. but precisely because it goes with dissipation. That's why we observe this object as bright bursting sources, hot stars like ambipolar diffusion heating the core, and mechanical dissipation through plastic flow in the crust, plus possibly ionic heating in the crust. They make the surface of the star hotter than it would normally be. There are also particle magnetospheric dissipation, which occurs because the magnetic helicity gets out of the star, it generates electron-positron discharge in the twisted magnetosphere. These particles accelerating in the magnetosphere bombard the star, create hot spots, and we observe them. And also, if you over-twist the magnetosphere, finally, the magnetic chunks of magnetic energy have a chance to escape through explosive reconnection. A large part of it just moves out, freely expands from the star, but part of it is dissipated, and that's precisely the dissipated part that we see as bursts or giant flares in some cases. And finally, these explosions also launch blast waves into winds of the stars, of the magnetars, and these blast waves naturally have a coherent radio emission mechanism, which is so bright, so much easier to observe in radio band. The detectors, radio detectors, are so much more sensitive than even optical, not to mention X-rays detectors. So radio telescopes can pick up weak radio signals easily from very large distances, from distant galaxies. And actually, this coherent radio emission from blast waves from these flares are expected to be really bright and easily detectable. And so that may be why we are observing these fast radio bursts, simply because there is a population of magnetars that keep producing blast waves, and we easily pick up them in radio. Not so easily in X-rays, not even in gamma rays, but in radio, yes. And so I was arguing that these distant galaxies may have many young hyperactive magnetars, which we're missing in the Milky Way. Just statistically, we don't see a recently born magnetar, but they can exist in distant galaxies and producing separates. And I'll stop at this point. Thank you.
Well, thank you very much for a very nice presentation. We have some questions from the audience, so let's start with Efraim Ferrer.
Yes, thank you. Thank you for the interesting talk. I would like you to comment about the possibility to have magnetars with a strange matter, and also to talk a little more about how to get the stability of the field, of the high field that you can have in the core.
I cannot tell you much about it. I mean, it's possible. There could be there are works, of course, on the transition. You can have strange matter in the core. Things might depend, but I don't know what should happen then with the magnetic field. I don't think I'm in a position to make any predictions there. The only thing I can say is that a lot should depend on the mass, because the higher density. This may be this kind of transitions may depend on how massive the neutron star is. Well, you can imagine different classes of magnetars. If you create a really massive magnetar, let's say 2 solar masses or more, then it will be the most compact neutron star with very high central density, and then you can expect things more likely. There could be a transition there. So it would be interesting. It's possible that there are 2 types of magnetars, let's say. You see what I mean? And depending on their mass. Yeah. Another difference. Yeah. Another difference is that if the star is massive enough, so the density reaches 10 to the 15th grams per centimeter cube, then another qualitative difference that happens there, important for this dynamics that I described, is that you activate direct Urca process, which is much stronger neutrino cooling channel. And so basically, once you activate it at the center, you effectively cool the entire core, because the core is pretty much isothermal. The thermal conduction time scale across the core is very, very short. I mean, it's very good conductor, heat conductor. And so once you switch off direct Urca cooling in this massive star, you produce cool the core quicker, you accelerate ambipolar diffusion very much. So whatever activity comes out from it happens really quickly in these massive objects. And also, of course, they become quickly superfluid. Yeah, and so one can imagine different classes of magnetars. And phonologically, so far, I don't think there is much known, but hopefully with more data from fast radio bursts in particular, once this connection is completely established between cosmological fast radio bursts and magnetars, maybe we'll have more data to learn this kind of stuff phonologically. Theoretically, I don't think we're in a position to make predictions. That's my view. Okay.
Thank you.
Okay, next question from Stephen Harris.
Hi. So you mentioned at the very beginning that these flares from magnetars would cause these oscillations in the magnetar, and that could tell you something about the superfluidity inside of the magnetar. Do you know if they were able to determine if it was both the neutrons and the protons that were superfluid inside of the star, or if it was just one or the other?
Yeah, I think mostly it's just the mass that is coupled to the issue. There is how much mass is tied to the oscillating field lines. So it's mostly neutrons that is an issue there. So I think you can say that neutrons are superfluid. For protons, in fact, they are not likely to be superfluid, because if you look at the fields that I was talking about, 10 to the 16th Gauss, they are above the critical field that will quench proton superfluidity.
Okay.
Yeah, I mean, it depends on density. The critical field that suppresses superconductivity depends on density. And it's possible, and also field doesn't have to be uniform inside the neutron star. So it's possible that it suppresses superconductivity somewhere in the, but there are also normal pockets of protons. But anyway, so protons carry only like 10% or less of the mass. And so that, I think this, it is as far as I know from this analysis of oscillations, you can say about, draw conclusions about neutron superfluidity, probably not proton.
Okay, thank you.
Okay, any other questions? I do have a question of my own, though. You didn't really mention too much about this in your talk, but somehow in the summary, you kind of slipped that word, helicity of the magnetic field that escapes. And I assume it comes basically from the fact that you have this, you call them whistlers, sometimes people are calling them helicons. When they're coming out, this is basically helical magnetic fields. So what's the role of helicity in the in this outside perhaps regions of the magnetar? Is the helicity a player basically?
Well, helicity in this context, I think a useful kind of image of what the field is doing. If you think of it as a wound up spring hidden, buried initially inside the core, inside the neutron star. It's likely to be, by the way, mostly toroidal, because the field amplification was most likely helped by differential rotation during the neutron star birth. So there is a lot of azimuthal field, toroidal field created inside the star. And so after the birth, the star is endowed with this wound up field. It's like a spring, which would like to, just relax and get out. And so this helicity, it tries to escape. That's how, in the simplest picture, you have, when the field succeeds to unwind a little bit, you pass this winding from inside the star to the exterior of the star. That's what that helicity transfer process that I meant. And once it ends up in the magnetosphere, then you have a little resistance, because the magnetosphere, it does not easily sustain the electric current that you need to sustain this winding of the field. And so now you have a resistor and you have basic Coulombic dissipation. So the magnetic helicity transferred, the the helicity has been transferred from very conductive material to less conductive material. You need to create electron positron pairs to keep this twist in place. And so it has a finite lifetime, it dissipates over time.
Right. But wouldn't that imply that the emission of the photons in all the spectra will be polarized? Wouldn't you expect to see a polarized emission then?
Yes, the emission is polarized. It's not related to the global, this large-scale helicity in the field, but there are two polarization states of photons in strong magnetic field, the so-called X and O mode. So one has electric field perpendicular to the K wave number of the photon, and the magnetic field, local magnetic field, is the E mode. And the one has the other mode, electric field of the waves, is along that plane, KB plane. And so, yes, so there are these eigenstates, polarized states. And you do expect the emission to be polarized, which, by the way, will be probed with soon by polarization emission. We'll have polarization, X-ray polarization data soon. Yeah, it depends on, of course, it's going to be different depending on how you produce and where this X-ray escape. Yeah, so the polarization state actually adiabatically tracks as the photon propagates through the magnetosphere, and then at some point it decouples and it leaves polarization imprint on the observed spectrum. Yeah.
Right, right. I see. Very interesting. Any other questions from the audience? I do have another question I want to ask, but I don't want to just state my own questions. When you were talking about the ambipolar diffusion, primarily you were talking about the interaction between protons that carry current and neutrons that basically have, carry the moment of inertia. But what about the electrons? They should be carrying the current, and I assume they will be scattering of protons because they are moving in the opposite direction. There should be basically some diffusion there as well, no?
Yeah, the densities are so high, electron density in the core. So density is 10 to the, let's say, 14 grams per centimeter cube, like 3 times 10 to the 14 nuclear density. So yes, electrons are a small fraction of it, and protons, maybe 10%, but still it's a huge number density. So to sustain the electric current that supports that magnetic field, the drift speed of electrons is tiny with respect to protons. So in the core, these kind of effects, in particular, the Hall effect that I talked about in the crust, in principle, it also exists in the core because electrons are drifting with respect to protons. But because of high densities in the core, this effect is small. I mean, the drifts are not really important.
I see. So it's kind of on the contrary, because they are such good conductors, they don't have to move fast. That's what you're saying.
Yeah, because the densities are so high, it's sufficient to have a very small electron velocity to carry the electric current that you want.
Yeah. I see. I see. Okay, sounds good. Any other questions before we wrap this up? I don't see anything. So using this opportunity, I would like to thank again Andrei for a very nice presentation. It was kind of a lot of interesting physics all in one package. And I think audience agrees. I see the claps showing on the reaction. So thank you.
Right. Thank you very much.